So this is Gabriel Peitz. I've had the pleasure of working with him for the last couple of years in research. My son, it's been a privilege. He's a chemistry major, minor in biology. He's run track and cross country for 4 years. He's earned the Scholar Athlete of the Year in 2023 and Elite 18 Award in 2022. He's also involved in a lot of different clubs and will be graduating with his chemistry degree and moving on to a pharmacy program down at UNMC. And so here's his honors course. Congratulations.
Thank you.
Take it away.
Thanks for coming. So for my honors, we did a study of AZO-Dyes containing highly fluorescent components. And that's why I helped with Dr. Peitz and Ashley Shemick with this project. So first I'll talk about our purpose, and it was to study compounds that have interesting UV, vis, and fluorescent spectra. These are novel compounds that are created by coupling fluorescent compounds such as chloramines, aminoacronyns, naphthals, and anilins to create our colorful dyes. And once we created these, we studied their electronic and structural properties. Some electronic properties we studied were their absorbance and fluorescence spectra. We compared this to theoretical Spartan calculated data. And then the structural properties we studied were through IRs and NMRs. And the purpose why I did this was to learn advanced chemistry techniques and how to use all the instruments up at the 3rd floor chemistry. And so for a little background, I'm going to talk about the difference in between fluorescence and absorption. And so when electrons are in their normal state, they favor a low energy called the HOMO. That's indicated by this S0. This is the lowest energy state, and it's also called the highest occupied molecular orbital. It's occupied because that's where electrons are. And so depending on how the compound is conjugated and how many double bonds it has, it absorbs photons of different wavelengths. And once it absorbs it, it gets excited. This is called absorption, which is shown in the blue. And it goes up to a higher energy state, which is called the LUMO. It's lowest unoccupied molecular orbital. It becomes occupied once it gets excited. But then it doesn't like to be in this high energy state and will dissipate the energy either by vibrational relaxation or by fluorescence, which is what we're detecting. And so here, our fluorescence always goes from the LUMO to the HOMO. And so it should always be the same. And this was proof of concept in theory. So our blue is our absorbance. So our compound that we created here absorbs well at 210, 260, and 400. Really good at 260 there. And so the absorbance, and then once it goes back down, we excited it at that 210, 260, or 400, and then observe how it went back down through the instrument. And as you can tell, they all go from the HOMO to the LUMO, which is why they are all the exact same. So it's nice to see that in theory. And so here's our general reaction on how we created our novel compounds. So first we started with an aniline, or aminoacronym, and a beaker. And so we put some of that in there, and we put excess hydrochloric acid and sodium nitrite. And this reacted to create a diazonium salt intermediate with a positive nitrogen. And then in a separate beaker, we mixed our 7-hydroxy or naphthol. And this created an O- there, so we had a negative species. And it creates electronegative spots at A and B. And so that's where our diazonium salt will combine and form our AZO-Dye. It's called AZO-Dyes because the N double bond N is a azo bond. And then when I was talking about conjugated species with lots of double bonds, that's what all these are. The electrons can kind of move freely throughout the whole, all those areas. And so for our first reaction, we tried to combine our 7-hydroxycoumarin with 9-aminoacronym. And we did have some success with this. That's our possible product. And so here's the UV vises of it. The blue is our product, and then these are our reactants. So we were getting different product, but we were having troubles classifying it on the instruments we had at our lab. And as you can tell, it fluoresces really nicely, and started off yellow and it's kind of brown. So that was our initial one, but we're having troubles with it, so we decided to go to a simpler system. And so we combined our 7-hydroxycoumarin with different anilines. These are our anilines. And so we went from regular aniline to 4-chloroaniline to 3,4,5-trichloroaniline. We labeled out the T for tri, 4-chloro for, or C for 4-chloro, and then E for aniline, because we already used A in a different one. And so we wanted to see how the chlorines affected the electron, the UV vis and fluorescence, and if we could find a trend on how the chlorines affect the electronic or structural properties. And so first, we did the reactions, created our products, and purified them. And so, to purify them, we ran thin layer chromatographies. First, we did a small plate one, which is right here. We have our reactants on the first two, and then product on there. It's a little small, but the top, as you can tell, is different from where the reactants are. And so that's what we scraped off. We ran a large plate TLC, scraped off the possible products. Each one we grabbed 2 of them that we thought were possible products. And they probably were products, just isomers of each other attached at different spots on the 7-hydroxycoumarin. And so after we scraped it off, purified it through syringe filtration, we came up with these 6 products. B1, the normal aniline on the left, 4-chloro and then trichloro. And as you can tell, they all fluoresce really nicely. They are similar, but they do fluoresce slightly different, probably because they're isomers. And so here's the IRs of our reactants compared to our product. And so the top is our 7-hydroxycoumarin, which had an alcohol and a ketone on it. And then below that's our aniline, which has the NH2. Because that becomes an azo bond, it should disappear, and it does. And our 7-hydroxy still stays there with our ketone and alcohol group. And so that's good. We're having, shows proof that we're getting a product. Our ketone kind of moved to a different spot, which is expected. And so we tried to find a trend on how the chlorines affected the structural data first, and we could not find a trend. The ketone came up at different spots, and we couldn't figure out exactly why that was. We couldn't figure out any other possible trends. So we looked at the electronic properties of it. So this is our top cut, what we thought was good product, and as you can tell, we got peaks for our trichloro early at 340, and then our aniline and 4-chloroaniline had them at 440. Couldn't really find a trend there for the UV vises. And so here's the bottom cut, another possible product that we were getting, probably an isomer of it attaching to a different spot on the 7-hydroxycoumarin. And as you can tell, we still have the same peaks at 340 and 440. But again, no trend really, and our second cut of our trichloro didn't really have very good UV vis. And so we excited it at the early one, 220, which they all had a pretty good peak on, 340 and 440 to get the fluorescence of them. And we found that our trichloro systems did fluoresce, and then our B also fluoresced. And even though they look different, and I said that the LUMO to HOMO is always the same, it is because we excited it here at 220, so we were getting data from 240 up. But this one, since we excited at 340, our wavelength starts right there, but we're still getting that 400 peak. So the fluorescence is still the same. And because our fluorescence is lower than 440, we did not get any fluorescence at our last peak that we excited. So since we could not find a trend of our how the chlorines affected the UV vis and structural spectras, we decided to try to figure out which isomer we were getting. And so we focused on our 3,4,5 trichloro system and ran a plastic column to try to get a larger sample size so we could get more information on it. And so We ran a plastic column, separated them out, and then cut it and purified it. And so then we could try to find an NMR and then compare UV vis and fluorescence to computer calculated data to try to figure out which isomer we were getting. And we got 4 cuts. As you can see, the first 2 are similar and then the last ones are similar. Here's the actual column where we cut it and then purified it from. And so to try to figure out where the isomer was occurring, again, A and B was most likely, but it could be at C too. And so we ran a Spartan, which is a software for chemistry that'll give us theoretical information of our products. And we tried to compare that to what we were actually observing on the machine. So this was our instrumental information about our trichloro. And then the green peaks are our Spartan calculated theoretical peaks. And so we were getting the same peaks, which is good. It shows we were getting our product. B is the lowest energy, and so that would probably be most likely to have occurred. And so the first peak at 380 is our HOMO -1, so it's actually our second highest occupied molecular orbital, and when it gets excited it goes to the LUMO. And then at 420, that's the actual HOMO. Again, it gets excited to the LUMO. And B is the only one with a very good HOMO peak there. The other ones are small. So kind of tells us that we could be getting that because we do have a little peak there in our product. And so here's the actual molecular orbitals. Again, this is the HOMO -1. And as you can tell, they are all very similar. They're just isomers of each other. And so B has the most electron density spread out across it. The other ones are very similar, but we don't have a ton in our up top in this area. And then here's the HOMO orbitals, which our B had the best Spartan calculated peak, but it also has by far the best electron density spread out across the whole molecule. These ones not much in the aniline, and so that could be why it had a bigger peak. And they get excited to the LUMO, and that is the electron density of those. C actually has our best electron density. And so we weren't able to decisively say which isomer we were creating based off our T1. So that was kind of sad, but we did another study to see how the chlorines affected it. And so this one, we combined 1 naphthol with our aniline. Again, we have regular aniline, 4-chloroaniline, and 3,4,5-trichloroaniline mixed with our naphthol. And we weren't sure where it would be attaching, but A, B, C were our most likely spots. So after we ran it and purified it, we found the UV vises of each. And for this one, they are all very similar, but we did have a trend, which is blue shifting. So when we had just the regular aniline, our peak is about 510, and then the 1-chlorine created a peak around 500, and then 3,4,5-trichloro had a peak around 490. So blue shifted or shifted it towards a higher wavelength. We have very similar peaks down here too. They're all very similar. And then again, we had possible second products of this. And so here's those, but we did not have a trend on those, which kind of shows which isomer we have could be affecting our trend, and that for our other one, you might have been having the same isomer on position A for all of them, and that's why we observed the blue shift. But for this one, the only trend really is that the chlorines actually made these 2 peaks into one. So this one has 2 humps there, and then a 4-chloro kind of evens it out, and then the trichloro just creates one little peak there. So that was interesting. And so we compared it to our Spartan calculated data to see if we could figure out which isomer we were getting. And position A was the lowest energy state, so it was the most favorable. Right there. And because we mix this with hydrochloric or sodium hydroxide, make this minus, A is a very likely spot. So we could have been having on our first cut very pure products on that. And so here's our Spartan calculated absorptions compared to our actual absorptions in the lab. Our black line is our absorption found in the lab, and this is our theoretical. And again, the first one is the HOMO -1, and then the HOMO, they all get excited to the LUMO. And A is actually our lowest energy state and fit our actual absorption very well compared to the rest. This second peak, the HOMO to the LUMO, is a little off, but it has the same peaks at 350 and 300 compared to these ones. We're just completely off. So based off this, we were probably getting our product on A, so that was a positive on that one. And so for future ideas and some of the difficulties we had on this, we had good electronic data, which was our UV vis and fluorescence of each, but we would like to get more structural information, such as the NMR, but our NMR we have up in our lab is not sensitive enough. And so also some of the instrumental troubles we ran into is a mass spec, which would give us the mass of our product. And we could compare this to what we were hoping the mass, and you can see if we were getting our product, but we were unable to really get a mass spec. We have the GC mass spec up there, and our product was probably getting caught up in the column and not coming out smoothly, so we weren't getting good information on that. And then we got a brand new UPLC, ultra pressure liquid chromatography, and it also has a mass spec on it, but half the year it was getting built, and then the rest of the year we just had troubles getting exactly our product or getting a good mass spec out of it. And so for the future, hopefully we can work with some of our state colleges and use their NMR and figure out the actual structural information of our products. And bibliography. Here's a shirt of all our dyes too that I tie-dyed, just for the fun of it. It kind of fluoresces if you have a black light to it, but our compounds weren't exactly safe, I would say, and plus it dye your skin, so not recommended to wear.